Okay, so in the previous video we discussed the infinite power tower, root 2 to the power of root 2 to the power of root 2 to the power of root 2 all the way ad infinitum, and whether or not it converged. And depending on which way the brackets go and which way you do the calculation, it either does or it doesn't. And assuming that we do the brackets this way down, then it does converge, and it converges to 2. And I promised you that we would look at the proof that the sum, that this expression equates to 2. And it's quite good fun, these infinite power towers. And in fact, I said in the previous video that infinite power towers were quite good fun. And I got a text from someone who shall remain nameless that A, do I have a dictionary? And B, if so, have I ever looked at the definition of fun? Very funny. Okay, so the proof that root 2 to the power, root 2 to the power, root 2 to the power, root 2 ad infinitum is equal to 2. So to actually do the proof rigorously, we need to deal with the Lambert W function, but we're not going to do that yet. We're going to do that in a subsequent video. So at the moment we're going to do 3 proofs, which are not quite as rigorous, but they still do prove. So method 1 actually involves knowing that we want to prove this, so we actually do it from the other way round. X to the x to the x to the x ad infinitum equals 2. So we need to know sort of that the result is 2. So we want to go so x to the power of x to the power of x to the power of x ad infinitum equals 2. So from that we can say that we can take logs. So the log of x to the power of x to the power of x to the power of x ad infinitum equals the log of 2. Now this bit here is the power, and by using our logs we can move that out to here. So that would be x to the power of x to the power of x log x equals log 2. But we know from the question that x to the power of x to the power of x ad infinitum equals 2. So therefore we can now put that 2 log x equals log 2. And from that we can say that log of x squared equals log 2. And from that we can say that x squared equals 2. So therefore x equals root 2. We can ignore the negative. So that's the first method. And we have proved that the infinite sum, the infinite tower here, for x to the power of x to the power of x equal to 2, we know therefore that x must equal root 2. So that does prove it, sort of, although we do need to know the answer. So let's have a look at method 2. Method 2 is by induction, and method 2 also doesn't actually prove that it does equal 2. It just proves that it converges to something less than 2, and we do that by induction. So let's just say that we have a tower. A to the k is root 2 to the power of root 2 to the power of root 2 k times. And let us assume, as this is induction, that a to the k is less than or equal to 2. So now let's have a look at a to the k plus 1. So a to the k plus 1 is root 2 to the power of a to the k, because a to the k is root 2 to the power of root 2 to the power of root 2 k times. And so adding a root 2 gives us a to the k plus 1. But we know that a to the k is less than or equal to 2, or we assume that it is. Now, if a to the k is less than or equal to 2, then root 2 to the power of a to the k is less than or equal to 2, because root 2 to the power of 2 is equal to 2. So therefore, root 2 to the power of a to the k, which is less than or equal to 2, must be less than or equal to 2. So therefore, assuming that it is true for ak, then it is also true for ak plus 1. Now all we need to do to complete the induction proof so that it is less than or equal to 2 is look at a1. Well, a1 is root 2, which is clearly less than 2. And so therefore we have proved by induction that that the expression root 2 to the power of root 2, the infinite power tower, is less than or equal to 2. Okay, so we sort of skirted around the issue here. We haven't really actually proved that it's 2. We've proved that it's less than 2, and we've also proved that if we know the answer is 2, then we can get root 2 as being the power tower. So method 3 is slightly more formal. So let's take our root 2 to the power root 2 to the power root 2 to the power root 2, blah, blah, blah. Let's call it equal to a. So i.e. a is equal to root 2, and here that is equal to a, because that's the infinite power tower as well. So a is equal to root 2 to the power of a. So taking logs, we have log a equals a log 2, which equals a log root 2, which equals a log of 2 to the half. So now let's move the a down to the other side, and we have 1 over a log a equals log of 2 to the half. And we can now move this in here, again by basic logs. And so we have log of a to the 1 over a equals log of 2 to the half. And now when we look at a to the 1 over a and 2 to the half, we clearly have one solution to that by inspection. One solution is a equals 2. So going back all the way to here, we have proved that root 2 to the power root 2 to the power root 2 ad infinitum equals 2. There is actually another solution to this though, which is 4. If we look at this and we put in by inspection a equals 4, 4 to the power of a quarter is the same as 2 to the power of half. So there is an alternative solution to this, which is a equals 4, but we know from method 2 that the sum of the infinite power tower must be less than or equal to 2. So in actual fact we can ignore the solution a equals 4, and therefore method 3 does give us the correct answer, that root 2 to the power of root 2 to the power of root 2 ad infinitum equals 2, and there's